Exercise 23.7 is asking us to rank three fairly similar looking molecules in order of increasing basicity, so from the least basic to the most basic. Now we talked a little bit about the basicity of these amines in the previous video, and you'll notice that each of these are amines. You have nitrogens with no carbonyls around them, and so that's an amine. Now, on these, whenever you see an amine, you want to draw a lone pair on it. The lone pair often is not drawn in the structure, and yet it's responsible for so much of the reactivity and behavior of these amines. And when you draw them in, no sooner do you draw them in, but you notice that the lone pairs in all of these molecules are allylic to pi bonds. They are one atom away from atoms in double bonds, in both directions, and that's true for all of these three molecules. And the significance of that is that these pi bonds have parallel p orbitals to create the pi bond. And so those parallel p orbitals could go all the way around the ring, and this lone pair would be included in that. And so theoretically, the lone pair could be spread out over all of these atoms. And in fact, that happens, but it happens in all three of these molecules. You'll notice that what they have in common, all three of these molecules have this middle feature of the molecule in common. Benzene ring on one side, the amine with the methyl group going up, and a benzene ring on the other side. So what's really different, what will really change the basicity of each of these amines are the groups that are coming off of these carbon chains. That's what's going to change the basicity of these as you go from one molecule to another. Excuse me, now those chains are on aromatic rings. And so it will become important whether they activate those rings or deactivate them. First, let's take these molecules and let's order them separately, sort of separate them so that we can think about them a little bit more clearly. Excuse me. Now, in the previous chapter, the aromatic substitution chapter, we talked about branches on benzene rings, and we came up with this table. We went through a whole bunch of different groups, and we saw how some branches donate a lot of electron density to the ring. And this ring has electrons in it, a lot of electrons in it. And so if a group poured more electron density into the ring, then it activated that ring. And those were called activators, and we had strong, moderate, and weak ones. On the other hand, other groups could pull electron density out of the ring, and those were deactivators, and we had strong, moderate, and weak ones. So, let's classify each of these as activators or deactivators, strong, moderate, or weak, and then we'll be able to think about how that influences the basicity of the lone pairs on these nitrogens. Okay. So first, we have a bromine. Bromine is a halogen. It is a weak deactivator. That means that it is pulling electron density out of the ring. On the other side, we have an aldehyde. So carbon double bonded to oxygen on that benzylic position. So a pi bond to an electronegative atom that's conjugated with the ring. That was a moderate deactivator. Notice that it's conjugated with the ring. You have double, single, double, so alternating double and single bonds. That's what it means to be conjugated. And it's a pi bond to an electronegative atom. Excuse me. And so that is another deactivator. That means that this group is also going to be pulling electron density out of the ring. Let me actually show that. Okay. Now in the structure in the middle, it doesn't have any branches. The benzene rings don't have any branches at all. So nothing to think about there. At the bottom, we have branches, and both of the branches are alkyl branches. They're methyl branches. They're alkyl groups. So hydrocarbon chains. Those are weak activators. And weak activators push electron density into the ring. So these are pushing electron density into the ring. Okay, so now let's think about the lone pairs on these nitrogens and how basic they are. The more that this charge is pushed onto the nitrogen, the more basic the nitrogen is going to be. If electrons are being pushed onto the nitrogen, then the nitrogen is feeling a lot of negative charge around it, and it's going to want to rip off an H plus from another molecule to stabilize that. In other words, it's going to be a stronger base. Now, the nitrogen of these three that has the most electron density swirling around it is this bottom one, because the activating groups are pushing electrons onto the nitrogen. They're pushing it toward the nitrogen, and so the nitrogen feels all these electrons, feels so many electrons, all this negative charge, so it snatches an H plus from another molecule, and that is the strongest base in these three. On the other hand, at the top, these deactivating groups are electron withdrawing. They steal electron density away from the nitrogen, so the nitrogen feels less negative charge. And that means it's less likely to attack an H plus on another molecule, and it's the weakest base of these three. And of course, in that case, this molecule that has no branches on the benzene rings would be in between. It would be a stronger base than this one on top, but it would be a weaker base than this one on the bottom. So when we were trying to think about the basicity of the amines, the basicity of the lone pair on the nitrogens in these molecules, we noticed that the lone pairs, well, first we drew them in, then we noticed that they were allylic to pi bonds, and indeed to long conjugated pi systems, so that the lone pairs could spread out over a lot of atoms. But that was true for all three of these molecules. That's what we determined in the brown highlighting. So although that stabilizes the amine, it won't let us tell the difference between these three amines because they all have that stabilization. So to tell the difference between them, we had to look at the branches on the benzene rings. We had to remember how to tell whether those branches were activators or deactivators, electron donors or electron withdrawers. The activators donate electron density, push electrons toward the nitrogen, and make it more basic, more likely to attack an H+. The deactivators, the electron withdrawers, pull electrons away from the nitrogen, make it less negative, and make it less likely to attack an H+. And so it's a weaker base. And this one with no branches at all was in between. So here we used the activators and deactivators we learned in that previous chapter of aromatic substitution reactions. We used that concept to explain the behavior of the basicity of these three amines.